Hello, my friend. Welcome. Whether you're here for the first time or returning, you've just arrived in a calm corner of the universe. This video is meant to carry you gently into sleep while you learn. Tonight, we'll drift through the invisible world of atoms, the tiny foundations of reality. Settle in, let go of the day, and allow the story of science to become the background music of your dreams. Chapter 1. Atoms, the invisible foundations of reality. Everything you can touch or see is built from structures so small that visible light cannot resolve them. Yet the rules that govern those structures determine the texture of everyday life. To understand atoms is to understand why matter takes stable form, why colors appear and fade, why metals conduct electricity while glass does not, and why your body persists long enough to think about any of these questions. The word atom began as a philosophical conjecture about indivisible building blocks of nature. Modern physics both fulfills and revises that intuition. Atoms are not indivisible, yet they are fundamental to how reality presents itself at human scales. They anchor a bridge between the deep quantum world and the macroscopic world of materials, biology, and technology. Chemistry in the 19th century transformed atoms from speculation into measurement. Regular combining ratios in reactions, the conservation of mass, and the reproducible weights of gases all pointed to the existence of discrete units of matter. John Dalton's atomic theory gave these patterns a clear interpretation by proposing that elements consist of identical atoms that neither appear nor vanish in reactions, but merely rearrange into new compounds. Soon after, studies of electricity added another clue. Matter and charge seemed connected in a granular way, hinting that the constituents of matter might carry discrete packets of electric charge. By the turn of the 20th century, experiments with discharge tubes revealed the electron as a real movable particle with a well-defined charge-to-mass ratio. Rutherford's gold foil experiment then demonstrated that nearly all of an atom's mass and positive charge resided in a tiny central nucleus, with electrons surrounding it. Yet this classical picture was unstable. Orbiting charges should radiate away energy and spiral inward. Atoms plainly do not collapse, so something deeper than classical mechanics was at work. Quantum theory provided the needed framework. Niels Bohr's model imposed discrete orbits and quantized energies to reproduce the observed spectral lines of hydrogen. Though incomplete, it pointed the way to the fuller quantum mechanics developed by Schrödinger and Heisenberg. In this picture, an electron bound to a nucleus is described by a wave function whose squared magnitude gives the probability of finding the electron at a particular place. These wave functions form orbitals, standing wave patterns with characteristic shapes. They are not literal paths, but probability landscapes sculpted by the attraction between electron and nucleus and the rules of quantum mechanics. A typical atom is about 1/10 of a nanometer across, while its nucleus is 100,000 times smaller. Almost all the mass is packed into that nucleus, built from protons and neutrons. Those nucleons are composites of quarks held together by gluons through the strong nuclear force. Electrons, by contrast, are elementary within the Standard Model. They carry negative charge, intrinsic angular momentum or spin, and a magnetic moment that couples them to fields. The number of protons fixes the element's identity, while neutrons tune stability through isotopes. If atoms are mostly empty space, why does matter feel solid? Two principles cooperate to provide solidity. The first is electromagnetic repulsion among electron clouds, which becomes strong when they overlap. The second is the Pauli exclusion principle. Identical fermions cannot occupy the same quantum state. When atoms approach closely, their electrons cannot all settle into the lowest arrangements, and the energy cost rises steeply. This quantum mechanical rule is the reason your hand does not pass through a table, even though both are nearly all nothing. Atomic identity stems from the number of protons, the atomic number. Isotopes differ only in neutron count and usually share chemistry while varying in mass or stability. This division of labor, protons for identity, electrons for chemistry, arises because the electromagnetic force governs interactions at the atomic scale. When electrons fill orbitals in multi-electron atoms, the picture becomes richer. Repulsion between electrons and their spin properties shape how orbitals are occupied. These patterns explain the recurring structure of the periodic table. Noble gases with filled valence shells are inert. Alkali metals with a single outer electron are reactive. Halogens, one electron short of a filled shell, attract electrons strongly. These recurring families of behavior are consequences of quantum structure, not arbitrary classification. Spectroscopy made atomic physics precise. Atoms emit and absorb light at discrete wavelengths corresponding to transitions between quantized energy levels. Each element has a fingerprint spectrum, allowing scientists to identify substances on Earth and in distant stars. Subtle splittings in spectral lines, such as fine and hyperfine structure, reveal interactions between electron spin, orbital motion, and nuclear magnetism. Measurements of tiny shifts like the Lamb shift, which arise from fluctuations of the quantum vacuum, demonstrate the extraordinary accuracy of quantum electrodynamics. That theory and experiment agree to many decimal places is one of science's proudest achievements. Atoms also underpin timekeeping. The official second is defined by a specific transition in cesium-133, and modern optical clocks based on strontium or ytterbium now push stability so far that they would drift less than a second over the age of the universe. Such clocks test whether fundamental constants change with time, measure gravitational time dilation between floors of a building, and support the precision of GPS systems. They show how the quantum regularity of atoms translates into practical control of reality. Direct visualization of atoms became possible in the 20th century. Transmission electron microscopes use electron waves short enough to resolve atomic spacings. Scanning tunneling microscopes measure the tunneling current between a sharp tip and a surface, mapping electron densities atom by atom. Atomic force microscopes extend similar principles to insulators by sensing forces with nanometer precision. These images are not photographs in the classical sense, but they provide reproducible maps of atomic landscapes, turning the invisible foundations of matter into tangible structures we can manipulate. Control over atoms has become astonishingly refined. Laser cooling slows atoms to microkelvin temperatures by using the momentum kicks from photons. Optical and magnetic traps then confine them, while optical lattices, standing waves of light, create controllable crystal-like environments. Such systems let scientists explore quantum phenomena in detail and test fundamental constants. In other contexts, trapped ions and neutral atoms serve as qubits for quantum computation, their delicate states manipulated by pulses of light and microwaves. The frontier of atomic physics today is not just measurement, but mastery. Atoms in solids reveal further structure. When atoms assemble into crystals, outer orbitals overlap and broaden into bands. Whether electrons can move freely through these bands determines if a material is a conductor, semiconductor, or insulator. This framework explains why metals conduct why semiconductors can be tuned into switches, and why insulators resist current. Modern electronics, from diodes to transistors, rests on this atomic-level understanding. Lasers, too, are atomic machines relying on stimulated emission from excited atoms or molecules. The language of atomic physics permeates the rest of science. Selection rules explain why some transitions are allowed and others forbidden. Spin-orbit coupling explains fine structure and underpins many properties of materials. External fields shift energy levels, providing tools for diagnosis and control. Even corrections from relativity and vacuum fluctuations become measurable with spectroscopic precision. Atomic physics thus stands not just as a foundation, but as a precise laboratory for testing the most fundamental theories. Atoms also serve as probes of the universe beyond Earth. The absorption and emission lines of elements in stars reveal composition, temperature, and motion. Interstellar hydrogen's 21-centimeter line maps galactic structure. Because laboratory wavelengths are known with extreme accuracy, shifts in astronomical spectra measure cosmic expansion and gravitational effects. Atomic physics thus links the laboratory to the cosmos, showing that the rules we uncover here apply across unimaginable distances. So are atoms fundamental? In one sense, no. Protons and neutrons are made of quarks, and even electrons are best seen as excitations of quantum fields. Yet in another sense, atoms are fundamental to our lived reality. The rules of quantization, superposition, and exclusion are what give matter its stability, colors, and capacity to form structures. Without atoms behaving as they do, stars would not shine steadily, chemistry would not follow a periodic rhythm, and life could not emerge. For a final reflection, remember that your body is a temporary arrangement of atoms forged in ancient stars, cooled by the expanding universe, and organized into patterns capable of sensing and remembering. When those patterns eventually dissolve, the atoms will persist, drifting into new structures and stories. The invisible foundations of reality are not only stable, they are the canvas upon which existence briefly paints its fleeting patterns. Chapter 2. Mostly Empty Space. Why Matter Feels Solid. When we imagine matter, we tend to picture it as something dense and continuous. A table looks solid, a stone feels heavy, and the floor beneath your feet seems unyielding. Yet when you descend into the scale of atoms, an astonishing truth appears. Almost all of what you call matter is empty space. The distance between the central nucleus of an atom and the outer regions where its electrons are most likely to be found is vast compared to their sizes. If an atom were magnified to the size of a cathedral, the nucleus would be smaller than a speck of dust suspended in its center. Everything else is void. And yet, this void somehow constructs the physicality you rely on, the sensation of a chair supporting you, the hardness of glass, the resistance of steel. To understand why matter feels solid despite its emptiness requires a deep exploration of the interplay between quantum mechanics and fundamental forces. The nucleus of an atom, composed of protons and neutrons, holds nearly all of its mass. It is a dense knot, only a few femtometers across. Surrounding it, electrons are not orbiting balls, but probability clouds described by quantum wave functions. These clouds stretch across a space tens of thousands of times larger than the nucleus itself. Within this architecture, the electron's actual presence is delocalized, meaning that you cannot point to a single definite place where it resides. What seems like a solid boundary when you imagine an atom is really a region of high probability, like a mist rather than a wall. Still, when two atoms approach one another, their clouds resist overlapping. This resistance is the foundation of solidity. One key principle is the Pauli exclusion rule. Electrons belong to the class of particles called fermions, each of which carries half-integer spin. Nature forbids identical fermions from occupying the same quantum state. This simple prohibition is one of the most powerful organizing rules of the universe. It ensures that electrons in an atom are stacked into distinct energy levels rather than collapsing into the lowest one. The exclusion principle is not merely an abstract rule, it has tangible macroscopic consequences. When you press your hand against a surface, the electrons in the atoms of your skin cannot settle into the same quantum states as those in the atoms of the surface. They are forced into higher energy configurations, and this rising energy creates a repulsive force that counters your push. You feel that resistance as solidity. Without this quantum law, matter would collapse into a featureless mass, stars would shrink into dense, degenerate objects, and chemistry would lose its structure. Electromagnetic interaction is the other pillar of solidity. Electrons carry negative charge, and nuclei carry positive charge. When two atoms come close, their electron clouds overlap and repel one another due to Coulomb's law. The magnitude of this repulsion grows rapidly with decreasing distance. At atomic scales, these repulsive forces are immense compared to the gentle pressure of your hand or the weight of a stone. What seems solid is, at its base, an electromagnetic negotiation between particles whose average positions are separated by spaces far larger than their own sizes. The interplay between attraction and repulsion defines equilibrium distances. In a molecule or crystal lattice, atoms sit at separations where the pull of electrons toward nuclei is balanced by the exclusion-driven repulsion of overlapping clouds. This balance point becomes the bond length in molecules or the lattice spacing in solids. Disturb that balance by compressing the atoms closer together, and the repulsion rises steeply. This is why materials resist compression. The cost in energy to squeeze atoms closer is enormous because it requires forcing fermions into already occupied states. At the macroscopic level, this quantum exclusion and electromagnetic repulsion manifest as mechanical properties. The hardness of diamond arises from the rigid covalent network of carbon atoms, each bonded with strong overlap-resistant electron pairs. Metals, on the other hand, feel solid but allow deformation because their electrons are not confined to individual bonds but roam collectively in bands, spreading repulsion in a more fluid way. Even gases, which have atoms widely spaced and moving freely, exhibit solidity when compressed. Their particles resist collapse because the same principles apply. Push them close enough, and their electron clouds push back with immense strength. It is striking that the sense of touch, one of our most immediate perceptions of solidity, is mediated by these invisible interactions. When your finger presses a surface, the atoms in your skin never truly touch the atoms in the surface. Instead, the repulsive forces between overlapping electron clouds and the rearrangement dictated by the exclusion principle create an effective barrier. Touch is the perception of electromagnetic force transmitted through nerves, not a contact of solid surfaces. In fact, in the deepest sense, no two objects in the universe ever truly touch. They approach, they repel, and the resulting force is what we feel. Understanding this emptiness also explains why matter can be penetrated by certain kinds of radiation. High-energy photons like X-rays can pass through tissues because they interact weakly with the electron structure, only occasionally scattering or being absorbed. Neutrinos, ghost-like particles created in nuclear processes, slip through entire planets because their interaction with matter is so faint that the emptiness of atoms is like open sky to them. The solidity that seems absolute to you is, in reality, relative, a property dependent on how different entities interact with the atomic landscape. This notion carries into astrophysics. White dwarfs and neutron stars provide cosmic laboratories for these principles. In a white dwarf, atoms are stripped of their electrons, and the matter is supported against gravitational collapse by electron degeneracy pressure, the collective resistance of electrons refusing to occupy identical states. In neutron stars, gravity overwhelms even that, forcing electrons to combine with protons and form neutrons. The exclusion principle then shifts to neutrons, whose degeneracy pressure holds the star up. In both cases, the same rule that prevents your hand from passing through a wall also holds up entire stars against collapse. The emptiness of atoms, coupled with the laws that prevent their collapse, becomes a universal guardian of structure. At more familiar scales, this emptiness is exploited in technology. Scanning tunneling microscopes rely on quantum tunneling, a process in which electrons cross gaps that would be insurmountable in classical physics. The tunneling current between a tip and a surface depends exponentially on distance, a direct reflection of the empty spaces between atoms. In semiconductors, the behavior of electrons in energy bands arises because of the overlap of atomic orbitals, again a balance of repulsion and exclusion, shaping how empty space between atoms becomes a medium for conduction. The gap between what seems solid and what actually exists is the realm of modern technology. The impression of emptiness within atoms also reframes the question of density. When we measure density macroscopically, we speak of mass per unit volume. For most materials, that volume is overwhelmingly empty. Yet because the nucleus is so compact and heavy, the density of nuclear matter itself is extraordinary. Billions of tons compressed into a cubic centimeter. The everyday materials you handle are tenuous shadows compared to that scale, their mass spread across spaces that are mostly void. The balance between nuclear compactness and atomic emptiness is what allows matter to be both stable and workable. Why then does the world not feel ghostly? Why does emptiness not dominate our experience? The answer lies in the scales of force. The repulsive barrier between atoms rises so steeply with distance that at human scales it behaves like a wall. You need not push very far before encountering resistance. This steepness is what translates vast emptiness into everyday solidity. A floor feels unyielding because any attempt to squeeze its atoms closer meets exponential energy costs, though between them lies more vacuum than substance. The counterintuitive nature of solidity reveals something profound about perception. Our senses evolved to interpret the results of forces, not the underlying structures. Vision detects photons emitted or scattered by atoms, but not the empty spaces between. Touch senses the nerve signals produced when electron clouds repel. We navigate a world of forces and interactions, not one of direct contact. The apparent solidity of the world is a translation of invisible quantum rules into human experience. Even more curious is that this perception of solidity is temporary. Atoms themselves are stable across cosmic timescales, but the arrangements they form, stones, mountains, your own body, are transient. Over millennia, atoms shift positions, bonds break and reform, materials weather away. What feels immovable is an arrangement of empty space stabilized for a moment by rules that prevent collapse. From a cosmic perspective, solidity is a brief phase in the flow of matter, arising from balance rather than from intrinsic density. The discovery of atomic emptiness and the principles that protect structure redefined our understanding of reality. What looks continuous and impenetrable is, at its heart, a void held together by rules. The laws of exclusion and electromagnetic force sculpt stability out of emptiness. Without them, the universe would be a fog of collapsed particles, lacking structure, shape, or life. And here lies the quiet, existential reflection. Everything that feels certain in your world, the floor beneath you, the air you breathe, the body you inhabit, is woven from emptiness, given solidity only by invisible rules. You are a structure of voids and forces, a pattern of resistance across spaces that are almost nothing at all. In the stillness of that realization is a kind of wonder. The solid world is less a substance than a balance delicate yet enduring, within which consciousness itself has briefly emerged. Chapter 3. The Quantum Dance of Electrons. Electrons are the restless actors of the atomic world. They define the chemistry of every substance, determine the colors of materials, and orchestrate the conductivity of metals and semiconductors. Their behavior is unlike anything in the macroscopic world. They are neither localized particles in the classical sense, nor continuous waves spreading indefinitely, but a fusion of both descriptions. This dual nature lies at the heart of quantum mechanics, and the movement of electrons around nuclei is not a mechanical orbit, but a quantum dance governed by probability, exclusion, and interaction. When scientists first attempted to explain atomic structure, they imagined electrons circling the nucleus like planets around the sun. This planetary analogy had a certain intuitive appeal, but it collapsed under scrutiny. Accelerating charges, as orbiting electrons would be, should radiate energy and quickly spiral into the nucleus. Atoms plainly do not implode, so another explanation was required. The breakthrough came when Niels Bohr proposed that electrons occupied discrete energy levels and could jump between them only by absorbing or emitting specific quanta of light. Though revolutionary, Bohr's picture was still an approximation. The real behavior of electrons emerged only with the full development of quantum mechanics, where electrons are described by wave functions rather than by orbits. A wave function is a mathematical entity that encodes all possible outcomes of measuring an electron's position or momentum. The square of its amplitude at a given point tells you the probability of finding the electron there. Instead of occupying a trajectory, the electron is spread out in a cloud of possibilities, an orbital. These orbitals have intricate shapes, spheres, dumbbells, clover leaves, emerging from the solutions of the Schrödinger equation. Each shape is not arbitrary, but reflects the balance between the attraction to the nucleus and the restrictions imposed by quantum rules. Where the wave function has nodes, the probability of finding the electron vanishes. These nodes carve the orbitals into regions of presence and absence, a quantum choreography etched into the architecture of atoms. This probabilistic view does not mean electrons are vague or unreal. Their distributions are measurable. Electron density maps, constructed from X-ray diffraction in crystals or from sophisticated quantum calculations, reveal the precise regions where electrons prefer to reside. These densities dictate how atoms bind, how molecules form shapes, and how materials display their properties. Electrons, though invisible, create the visible world by determining how light interacts with matter. The color of a gemstone, the transparency of glass, the sheen of metal, all trace back to electron transitions between quantized states. The Pauli exclusion principle plays a central role in this dance. Because electrons are fermions, no two can share the same quantum state within an atom. This rule forces them into layered structures, filling orbitals in a defined order and giving rise to the periodic table's recurring patterns. The inertness of noble gases, the reactivity of alkali metals, and the corrosiveness of halogens are not mere coincidences, but consequences of how electrons stack themselves. Every chemical reaction, from the rusting of iron to the metabolism in your cells, unfolds because electrons must find new arrangements that obey exclusion while minimizing energy. Electron interactions are not static. They vibrate, shift, and couple to their environment in dynamic ways. In molecules, electrons are shared between nuclei, forming covalent bonds, or transferred, creating ionic structures. In metals, valence electrons delocalize into a C, moving freely among positive ions and enabling conduction. In semiconductors, the delicate structure of electron bands allows currents to be switched on and off, the foundation of modern electronics. In each case, the apparent solidity or utility of a substance arises from the ceaseless motion of electrons, guided not by mechanical laws but by quantum rules. The quantum nature of electrons also explains magnetism. Electrons carry intrinsic angular momentum called spin, and each spin generates a tiny magnetic field. In most materials, the spins pair off and cancel, leaving no net magnetism. But in ferromagnets, unpaired spins align collectively, creating large-scale magnetic fields strong enough to move compass needles or lift iron. Antiferromagnets and ferrimagnets reveal subtler arrangements where spins oppose or partially align. Even in diamagnetic materials, electrons adjust their motion slightly to resist applied fields. All these magnetic behaviors arise from how the quantum properties of electrons couple to external influences. Light interacts with electrons in equally striking ways. When an electron absorbs a photon, it can leap to a higher energy level, only to fall back and emit light later. This process underpins fluorescence, phosphorescence, and the operation of lasers. In semiconductors, electrons excited across a band gap create electron-hole pairs whose recombination produces light in LEDs. The rules of these transitions are strict. Only certain jumps are allowed, dictated by conservation laws of angular momentum and symmetry. Yet, within those rules, electrons give rise to the full palette of colors seen in the natural and technological world. Modern experiments allow scientists to watch electrons in motion on ultra-fast timescales. With attosecond pulses of light, flashes lasting billionths of a second, it is possible to capture electrons tunneling out of atoms or rearranging during chemical reactions. Such measurements reveal that the electron's dance is not a metaphor, but a literal dynamic, unfolding faster than the blink of an eye, yet setting the tempo for processes as varied as photosynthesis, conductivity, and vision. In solids, the collective behavior of electrons produces phenomena that defy classical intuition. Superconductivity occurs when electrons, normally repulsive, pair up through subtle interactions with vibrations of the lattice. These pairs move coherently without resistance, allowing current to flow indefinitely. Quantum Hall effects arise when electrons confined to two dimensions under strong magnetic fields organize into states where conductivity is quantized in exact steps. These effects are not exotic curiosities. They represent the macroscopic manifestations of quantum order. They show how the dance of electrons, when extended across many particles, creates entirely new states of matter. The probabilistic nature of electrons also brings limitations to knowledge. Heisenberg's uncertainty principle tells us that we cannot know both position and momentum with arbitrary precision. For electrons, this means confinement in space comes at the cost of increased momentum uncertainty. The very existence of atomic size is set by this balance. Electrons cannot collapse into the nucleus because being so tightly confined would demand impossibly high momenta. Instead, they spread into orbitals, stabilized by the trade-off between attraction and quantum uncertainty. This interplay of rules ensures that atoms have structure and that the world has texture. In chemistry, electron rearrangements underpin every transformation. Breaking and forming bonds is nothing more than electrons finding new configurations that lower total energy. Catalysts work by offering pathways where electron densities shift more easily, reducing barriers. Enzymes in biology achieve the same by shaping environments where electrons can tunnel or transfer efficiently. Even processes like smell and taste involve subtle interactions of electrons with receptors, sensitive to shapes and charges carved by quantum distributions. Electrons, though light and elusive, are the authors of complexity. Their importance extends to astrophysics. The spectra of distant stars are fingerprints of electron transitions in atoms and ions. By studying these patterns, astronomers determine composition, temperature, and velocity. The glow of nebulae, the colors of galaxies, and the absorption lines imprinted on starlight as it passes through interstellar clouds all trace back to electron behavior. Even the cosmic microwave background, the faint afterglow of the Big Bang, carries signatures of when electrons combined with protons to form neutral atoms, allowing light to travel freely for the first time. Electrons are also central to our understanding of energy. Chemical energy, released in reactions, is stored in the potential arrangements of electrons. Electrical energy powering cities is the motion of electrons in conductors. Even nuclear energy, though rooted in forces within the nucleus, ultimately manifests through interactions with surrounding electrons, as radiation ionizes atoms and triggers cascades of electronic changes. The ubiquity of electrons in energy transformations makes them inseparable from daily life, even if they remain unseen. Despite their ubiquity, electrons resist intuitive description. They blur the categories of particle and wave, behaving as one or the other depending on how they are measured. In double-slit experiments, single electrons create interference patterns, as if each one explores multiple paths simultaneously. Yet when observed, each electron arrives at a definite point, never in pieces. This paradoxical duality is not a flaw of theory, but a fundamental feature of reality. It shows that the dance of electrons is not merely hidden from us, but intrinsically probabilistic. And yet, from this strangeness arises order. The properties of water, the structure of DNA, the functioning of neurons, all rest on the predictable arrangements of electrons. At scales large enough for life, probabilities average into reliability. The uncertainties of individual electrons blur into the stabilities of molecules and cells. What is unpredictable in detail becomes dependable in bulk, and from this dependability emerges the familiar world. For a final thought, consider what this means for you. Every sensation you experience, the light entering your eyes, the sound vibrating your eardrums, the warmth on your skin, begins as electrons shifting in response to energy. Every thought in your brain is an electron dance within networks of neurons. The solidity of your body, the chemistry of your cells, and the electricity of your nerves are all patterns sculpted by electrons moving according to quantum rules. You are, in the quietest sense, the choreography of countless tiny dancers, each uncertain alone but together composing the certainty of a living being. Chapter 4. The Forces that Hold the Universe Together. Every structure in the universe, from the smallest atom to the largest galaxy cluster, exists because of forces. Without them, particles would drift independently, never binding into nuclei, atoms, molecules, or stars. Yet the variety of phenomena we observe is not governed by an infinite number of different interactions, but by a handful of fundamental ones. Atomic physics, in particular, is a story of how these forces operate at tiny scales and how their delicate balance creates the stable reality we inhabit. The first of these forces is electromagnetism, which binds electrons to nuclei and gives atoms their size, shape, and chemistry. Electromagnetic attraction between opposite charges keeps electrons tethered near the nucleus, preventing them from escaping into the void. At the same time, repulsion between like charges shapes the structure of matter, ensuring that atoms do not collapse into one another. This force acts across distances that are vast compared to the scale of nuclei and governs nearly everything you can see or feel. The behavior of light, the functioning of your nervous system, the chemistry of water, all arise from electromagnetic interactions. Yet electromagnetism alone cannot explain why protons and neutrons remain bound together in the nucleus. Each proton carries positive charge, and by Coulomb's law, they should repel strongly enough to tear any nucleus apart. What holds them together is the strong nuclear force, a powerful but short-range interaction that operates at distances of about a femtometer, a trillionth of a millimeter. At that scale, the strong force overwhelms the electromagnetic repulsion, binding protons and neutrons tightly. It is the glue of atomic nuclei, and without it, there would be no stable atoms at all, only free protons and neutrons drifting separately. The strong force is remarkable not just for its intensity, but also for its subtlety. It is not a simple attraction like gravity or electromagnetism. Instead, it arises from the interactions of quarks, the fundamental constituents of protons and neutrons, through the exchange of gluons. Quarks carry a property called color charge, and gluons mediate the dynamics of this charge, confining quarks so tightly that they are never found alone in nature. This confinement explains why protons and neutrons appear indivisible in most circumstances. The residual effect of these quark-gluon interactions is what binds nucleons together in nuclei. It is a force strong enough to power the fusion reactions in stars, releasing the energy that sustains sunlight and creates new elements. Alongside the strong force is the weak nuclear interaction, which operates at subatomic scales but has profound consequences for the universe. The weak force allows neutrons to transform into protons and vice versa through processes such as beta decay. Though feeble compared to the strong force, it plays a vital role in nuclear reactions that occur in stars. In the early universe, the weak interaction set the balance between hydrogen and helium during nucleosynthesis, shaping the chemical composition of the cosmos. Without it, the universe would contain a very different mixture of elements, and the pathway to life as we know it might never have opened. The weak force is also central to radioactivity on Earth, influencing geological heat, medical imaging, and even the evolution of life through occasional mutations caused by natural radiation. And then there is gravity, the force that governs the architecture of the cosmos on the largest scales. Gravity is by far the weakest of the four, so weak that at atomic scales it is negligible compared to the other interactions. An electron is held to its nucleus by electromagnetism with a strength that dwarfs its gravitational attraction by factors of trillions upon trillions. Yet because gravity is always attractive and acts across infinite distances, it dominates at large scales, drawing stars into galaxies, galaxies into clusters, and clusters into the filaments of the cosmic web. While gravity does not directly shape atomic physics, it is the stage upon which atomic matter builds larger structures. The atoms themselves owe their existence to nuclear and electromagnetic forces, but their assembly into planets, stars, and galaxies is orchestrated by gravity. In atomic physics, these forces intertwine. Electromagnetism shapes the shells and orbitals of electrons, producing the periodic table and the chemistry of life. The strong force stabilizes nuclei, ensuring that atoms exist at all. The weak force, though subtle, allows nuclear transmutation, enabling stars to fuse elements and seeding the universe with diversity. Gravity ensures that matter once formed coalesces into structures capable of sustaining stars long enough for complex chemistry to flourish. Together, these forces create a coherent universe where matter is not only possible but persistent. To appreciate the balance among these forces, consider what would happen if their strengths were even slightly different. If the strong force were only a few percent weaker, nuclei larger than hydrogen might not exist, and the periodic table would vanish after its first entry. If it were much stronger, almost all hydrogen would fuse into heavier elements in the early universe, leaving no fuel for stars like the sun and no water for life. If electromagnetism were significantly stronger, atoms would be smaller, bonds tighter, and chemistry unrecognizable. If it were weaker, electrons might not bind effectively, and stable atoms might fail to form. Even gravity, despite its weakness, must be finely balanced. Too strong, and the universe would collapse rapidly. Too weak, and matter would disperse too thinly for stars and galaxies to ignite. The universe you inhabit is not just made by these forces, it is delicately tuned by them. Within atoms, the balance between strong and electromagnetic forces is particularly striking. The nucleus exists in a constant tension between the electromagnetic repulsion of protons and the binding power of the strong force. This competition sets the limits of nuclear stability. Light nuclei such as hydrogen and helium are tightly bound and stable. Heavier nuclei like uranium sit on the edge of instability, their large numbers of protons stretching the strong force to its limit. Beyond a certain point, no stable nuclei exist, and atoms with very high atomic numbers decay rapidly. Thus, the periodic table itself, the diversity of elements, emerges directly from the tug-of-war between these two fundamental interactions. The weak force, though often overshadowed, quietly enables cosmic evolution. It governs the lifetimes of neutrons, which outside nuclei decay in minutes. Inside stars, it initiates the chain reactions that fuse hydrogen into helium, a process that powers stellar luminosity. Without the weak interaction, the sun would not shine steadily but would either fail to ignite or burn too violently to support life on Earth. The existence of long-lived stars is therefore not an accident, but a consequence of this subtle force. It is the quiet hand shaping cosmic history, making time itself habitable. The electromagnetic force extends beyond binding electrons and nuclei. It also governs the behavior of light, which is the carrier of electromagnetic energy. Photons interact with charged particles, enabling atoms to absorb and emit radiation in discrete quanta. This is why we see spectral lines when starlight is dispersed, why neon lights glow with vivid colors, and why photosynthesis begins when chlorophyll absorbs photons. Electromagnetism not only structures matter, but also allows energy to move across space, linking atoms to one another and to the wider universe. Modern physics has unified some of these forces into broader frameworks. The electromagnetic and weak interactions are now understood as different aspects of a single electroweak force. which reveals itself at high energies in particle collisions. This unification demonstrates that what appears distinct at everyday scales may be facets of a deeper reality. Efforts to unify the strong force with the electroweak and ultimately with gravity remain unfinished, but they represent the search for a single coherent picture of all interactions. Such a theory would explain not only how atoms exist, but why the universe has the structure it does at every scale. The forces that hold the universe together are not abstractions. They manifest in tangible ways in your life. The solidity of the chair you sit on is a consequence of electromagnetic repulsion balanced by quantum exclusion. The warmth of the sun on your skin is the product of nuclear fusion driven by the strong and weak forces. The ground you stand upon, the earth itself, exists because gravity gathered atoms together into a planet. Each sensation, each experience, is made possible because these forces cooperate across scales so different that it defies easy intuition. And yet, for all their precision, these forces also invite reflection. Why should the universe possess exactly these four interactions? And why should their strengths fall within the narrow ranges that allow complexity? No one has a definitive answer. What can be said is that without them, or with even slight variations in their balance, reality as you know it would dissolve. In the empty quiet of this realization lies a sense of fragility and awe. The solidity of your world rests on invisible threads of force, woven across space and time, threads that are at once unimaginably strong and unfathomably delicate. Chapter 5. When atoms transform, radioactivity and decay. Atoms are not immutable. Though they are the fundamental building blocks of matter, under certain conditions they can change their very identity, transforming from one element into another. This process is radioactivity, the spontaneous decay of unstable nuclei, and it stands as one of the most powerful insights of 20th century physics. For centuries, people assumed that atoms were eternal and indivisible, but discoveries at the dawn of modern physics revealed a hidden dynamism at the core of matter. The nucleus, compact and dense, is not always stable. It can emit particles, release energy, and transmute itself. This instability, though invisible in daily life, shapes the Earth's heat, the chemistry of stars, and the very possibility of life. Radioactivity was first observed at the end of the 19th century, when Henri Becquerel discovered that uranium salts emitted mysterious rays that could fog photographic plates even in the absence of sunlight. Marie and Pierre Curie pursued this puzzle, isolating radium and polonium and demonstrating that radiation came from the atoms themselves, not from chemical interactions. This was a profound shift. Atoms were no longer indivisible, but reservoirs of internal energy. In the years that followed, scientists identified distinct types of decay, each revealing something about the structure of nuclei and the forces at play within them. Alpha decay occurs when a nucleus emits a cluster of 2 protons and 2 neutrons, essentially a helium nucleus. This process reduces the atomic number by 2 and the mass number by 4, moving the atom down the periodic table. Alpha particles carry high energy but are relatively heavy and can be stopped by a sheet of paper or even the outer layers of skin. Yet they are biologically hazardous if emitted inside the body, where they can disrupt tissues on a cellular level. The mechanism behind alpha decay lies in quantum tunneling. The alpha particle is bound inside the nucleus by the strong force, but simultaneously repelled by the electromagnetic force of the positively charged protons. Although classical physics predicts it should never escape, quantum mechanics allows a small probability that the particle will tunnel through the barrier. Over time, this probability ensures emission. Beta decay is more subtle. In beta-minus decay, a neutron inside the nucleus converts into a proton, emitting an electron and an antineutrino. The atomic number increases by 1, creating a new element. In beta-plus decay, a proton converts into a neutron, releasing a positron and a neutrino. These processes are governed by the weak nuclear force, the only interaction capable of changing the flavor of quarks inside nucleons. Beta decay was central to the realization that neutrinos exist. Early measurements showed that electrons from beta decay carried a puzzling spread of energies, which seemed to violate energy conservation. Wolfgang Pauli proposed the existence of an unseen particle carrying away the missing energy. This hypothetical neutrino was later confirmed experimentally, and it remains one of the most elusive constituents of the universe, streaming through matter with barely a trace. Gamma decay represents another dimension of transformation. After a nucleus undergoes alpha or beta decay, it may be left in an excited state. To relax, it emits a photon of very high energy, a gamma ray. Unlike alpha or beta particles, gamma rays are not matter but pure electromagnetic radiation, carrying energy across large distances. They penetrate deeply into materials, making them both useful in medicine for imaging and treatment, and dangerous as sources of radiation exposure. Gamma transitions demonstrate that nuclei, like atoms, have quantized energy levels. Just as electrons drop between orbitals and emit light of specific wavelengths, nucleons shift between nuclear states and release photons in the gamma spectrum. Beyond these main processes, there are rare transformations such as electron capture, where a proton in the nucleus absorbs an orbital electron and turns into a neutron, emitting a neutrino. This pathway alters the balance of protons and neutrons without expelling mass. Each of these transformations illustrates the delicate competition inside nuclei between the strong nuclear force which binds nucleons together and the electromagnetic force which drives protons apart. Stable isotopes exist where these forces balance, but as nuclei grow larger, instability becomes more likely. The heaviest natural elements, such as uranium and thorium, sit on the edge of stability, continually shedding particles to move toward more favorable configurations. The timescales of radioactive decay range astonishingly. Some isotopes decay in microseconds, flashing into new forms almost instantly. Others have half-lives measured in billions of years, persisting since the birth of the Earth. Carbon-14, with a half-life of about 5,730 years, provides a clock for dating archaeological artifacts as living organisms incorporate carbon from the atmosphere, then stop doing so at death. The gradual decay of carbon-14 then tells scientists how long ago a creature lived. Uranium-lead dating, based on the long half-lives of uranium isotopes, measures the ages of rocks and the Earth itself. These techniques reveal not only human history, but geological and cosmic history, showing that the transformations of atoms are also the record keepers of time. Radioactivity is not confined to laboratories or distant stars. It shapes the heat of the Earth, as the decay of uranium, thorium, and potassium in the crust and mantle produces geothermal energy that drives plate tectonics. Without this slow release of nuclear heat, the Earth might have cooled long ago, leaving its surface geologically inert. Volcanoes, mountain ranges, and even the magnetic field protecting our planet from solar wind all owe something to the quiet persistence of radioactive decay deep underground. In stars, transformations of nuclei take on even greater significance. Nuclear fusion, a process distinct from spontaneous decay but also involving changes of identity, powers stellar cores. Here, hydrogen nuclei merge into helium, releasing vast amounts of energy because the binding energy per nucleon is greater in helium than in hydrogen. In massive stars, this process continues, creating heavier elements up to iron. Beyond iron, where fusion no longer yields net energy, heavier elements are formed in the violent environments of supernovae and neutron star mergers. These cosmic events scatter newly forged atoms across space, seeding future stars, planets, and life itself. Thus, the transformations of atoms are not accidents. They are engines of cosmic evolution. In human hands, nuclear transformations have been harnessed with both constructive and destructive intent. Nuclear reactors rely on controlled fission, where heavy nuclei like uranium-235 split into lighter fragments, releasing energy and additional neutrons that sustain a chain reaction. This energy can generate electricity, but also produces long-lived radioactive waste. Nuclear weapons unleash this chain reaction without control, producing devastation on a scale unlike any chemical explosion. The same principles, though, also enable medical imaging and cancer therapy, where carefully targeted radiation destroys malignant cells. These technologies demonstrate that the power hidden inside atoms can be both a source of progress and a reminder of human responsibility. One of the most intriguing aspects of decay is its randomness. While half-lives describe predictable averages for large populations of atoms, the moment when a particular atom will decay cannot be foreseen. It is inherently probabilistic, another reflection of quantum mechanics. A lump of uranium may sit unchanged for years, yet at any instant one of its nuclei might emit an alpha particle. This unpredictability, scaled up to billions of atoms, produces the steady rates we can measure. But at its heart, it underscores that the universe is not deterministic in the classical sense. Even the building blocks of matter carry uncertainty in their transformations. Despite this unpredictability, the mathematics of decay is precise. Exponential laws govern the decline of radioactive substances, and these equations match observation with remarkable accuracy. This precision allows scientists to use isotopes as natural clocks, tracers, and energy sources. It also confirms that the probabilistic rules of quantum mechanics are not mere abstractions, but real laws shaping the course of matter across time. The discovery of radioactivity also reshaped our understanding of energy. Before it, energy was thought to emerge from chemical processes or physical motion. Radioactive decay revealed that within the nucleus lies a reservoir millions of times more energetic than any chemical bond. This insight led to the realization that mass and energy are equivalent, as expressed in Einstein's famous relation. When a nucleus decays, the slight difference in mass between the products and the original is released as energy. This principle explains why the sun shines, why reactors generate power, and why stars can resist collapse for billions of years. As research has progressed, new layers of complexity in nuclear transformations have appeared. Exotic modes of decay, such as double beta decay, where two neutrons simultaneously convert to protons, are now studied to probe fundamental symmetries of nature. Observing these rare events could reveal whether neutrinos are their own antiparticles, a discovery that would reshape our understanding of matter. In laboratories, scientists also synthesize superheavy elements beyond uranium, probing the limits of nuclear stability. Many of these atoms exist only for fractions of a second, but their fleeting appearance confirms the rules of nuclear structure and hints at an island of stability where heavier, longer-lived nuclei may yet be found. Even within living organisms, radioactive transformations play a role. Potassium-40, a naturally occurring isotope in bananas and in your own body, decays slowly, releasing radiation at levels too low to harm, but high enough to remind us that matter itself is never entirely static. Every second, some of the atoms that make up your tissues quietly transform, a reminder that even your own body is subject to the same processes that power stars and shape the Earth. Radioactivity also connects us to the deep history of the cosmos. The distribution of isotopes in meteorites carries signatures of nucleosynthesis in ancient stars. The decay of long-lived isotopes provides evidence of supernova explosions that seeded our solar system before it formed. By studying these isotopic ratios, scientists reconstruct the timeline of galactic evolution, reading in the transformations of atoms the story of how the universe became hospitable to life. For all its dangers and mysteries, radioactivity is not an aberration, but a natural expression of matter's instability. It reminds us that atoms, though foundational, are not eternal. They are subject to change, sometimes slowly, sometimes violently, but always according to the laws of physics. This dynamism gives rise to heat, light, and elements, weaving transformation into the fabric of reality. In closing, reflect on what this means for existence itself. The atoms that form your body are not immutable particles fixed for eternity. They are restless, some destined to decay, others to fuse in stars, still others to be remade in cataclysms light years away. You are built of matter that is both stable enough to endure and unstable enough to change. In this balance lies a profound truth. Solidity and permanence are illusions, while transformation is the deeper reality. You are, in a quiet sense, the temporary arrangement of atoms in mid-transformation, part of a cosmic cycle that began long before you and will continue long after. Chapter 6. Entanglement Inside the Atom. Among the most remarkable discoveries of modern physics is that particles are not always independent actors. They can share states in such a way that the condition of one cannot be fully described without reference to the other, no matter how far apart they may be. This phenomenon is called quantum entanglement, and it defies our ordinary expectations of separateness. While entanglement is often associated with distant particles linked across vast distances, its roots are found within the atom itself. The inner architecture of atoms provides some of the clearest natural examples of entangled states, and the stability and behavior of matter depend on this subtle interconnectedness. In atoms with more than one electron, the quantum states of those electrons cannot always be written as independent wave functions. The exclusion principle already requires that each electron occupy a unique quantum state, but when spin, orbital angular momentum, and energy levels are taken into account, the full description becomes inseparable. Two electrons in a helium atom, for instance, are entangled in their spins. If one is measured to be up, the other must be down. Their joint state is a singlet, a configuration with total spin 0, and it is indivisible. You cannot say that one electron is spin up and the other spin down in isolation. Rather, the atom holds a combined state that only makes sense when considered as a whole. This entanglement is not optional decoration but essential to stability. If both electrons in helium were allowed to occupy identical states, the atom would collapse into a configuration forbidden by quantum mechanics. By coupling their spins, the electrons maintain the required distinction while still minimizing energy. The atom's ground state is therefore a compromise written in the language of entanglement. Similar patterns occur in more complex atoms, where electrons pair up in orbitals, their spins linked to maintain compliance with the exclusion principle. The magnetic properties, spectral lines, and chemical reactivity of elements all depend on these entangled pairings. Entanglement within atoms extends beyond spin. The fine structure of atomic spectra arises from the coupling of electron spin and orbital angular momentum. These two properties, though conceptually distinct, are not separable in measurement. The total angular momentum of an electron is a quantum sum of both, and the resulting states are entangled mixtures. This coupling slightly shifts the energy levels of atoms, producing additional splittings in spectral lines. Such splittings were first observed as puzzling anomalies, but once understood, they became confirmations of quantum theory's predictive power. Here again, entanglement is not an exotic add-on, but a core feature of how atoms behave. Hyperfine structure offers yet another example. This arises when the magnetic field generated by electrons interacts with the magnetic moment of the nucleus. The spins of electrons and nucleons become linked, producing joint states that cannot be factorized. The famous 21-centimeter line of hydrogen, a crucial tool in radio astronomy, originates from a flip between hyperfine states where the electron and proton spins change from parallel to antiparallel. Without entanglement of electron and nucleus, this line would not exist, and one of astronomy's most powerful probes of galactic structure would be absent. Inside nuclei, entanglement is even more fundamental. Protons and neutrons are themselves bound states of quarks and gluons, whose colors and spins are so strongly coupled that the identity of one quark cannot be specified independently of the rest. The residual strong force that binds nucleons into nuclei relies on correlations among their spins and isospins. Models of nuclear structure, such as shell models and collective models, incorporate entangled states to describe how nucleons move in concert. The very stability of matter heavier than hydrogen emerges from the fact that nucleons are not simply independent particles, but correlated, entangled systems. Entanglement also provides a key to understanding chemical bonding. In covalent bonds, electrons shared between atoms exist in states that span more than one nucleus. Their wave functions are not localized to one atom or the other, but stretch across the bond. These electrons are simultaneously part of both atoms, and their spin states are often entangled, forming singlets that stabilize the bond. When molecules absorb or emit light, transitions often involve these delocalized, entangled electrons. The shapes and reactivities of molecules therefore cannot be explained without acknowledging that their electrons form collective states beyond classical separateness. Experiments have confirmed the presence and necessity of entanglement in atomic systems. Spectroscopic measurements of helium and other atoms show that their spectral lines can only be explained by joint states of electrons. Nuclear magnetic resonance, widely used in medical imaging, operates by manipulating entangled nuclear spin states in molecules. Even the operation of lasers depends on collective coherence of many atoms, a kind of macroscopic entanglement where photons and electrons act in unison. These technologies are reminders that entanglement, though strange to intuition, is embedded in devices and observations that touch daily life. The role of entanglement in atoms also highlights the limits of reductionism. While one might hope to describe each particle independently, quantum mechanics insists that in many systems the whole cannot be reduced to the sum of its parts. The atom is one such system. Electrons, protons, and neutrons often exist in entangled relationships that define properties not present in the constituents alone. Magnetism, spectral structure, and chemical reactivity are emergent features, not obvious from isolated particles. The atom is thus both a collection of particles and a unified quantum system, with entanglement as its connective tissue. From a more technical perspective, entanglement inside atoms reveals itself through correlations. If you measure one property of one electron, you gain knowledge of another property of a different electron, even before measuring it directly. These correlations violate classical expectations, but agree perfectly with quantum predictions. They are not matters of hidden communication, but expressions of shared quantum states. At small scales, atoms display these correlations continuously, even if they are not as dramatic as the famous thought experiments about particles separated by light years. Entanglement in atomic physics also bridges to quantum information science. Many proposed quantum computers rely on using trapped ions or neutral atoms as qubits. These qubits are not merely isolated particles, but entangled states whose correlations encode information. The fact that entanglement arises naturally inside atoms provides both opportunities and challenges. On the one hand, it demonstrates that atoms are excellent candidates for building quantum machines. On the other, it reminds us that controlling entanglement precisely is extraordinarily difficult because atoms are inherently coupled to their environments. It is important to distinguish entanglement from simple interaction. Two electrons may repel each other electromagnetically without being entangled, but when their quantum states become inseparable, entanglement emerges. This distinction emphasizes that entanglement is not just a force-driven correlation, but a structural feature of the quantum description. Inside atoms, forces provide the environment that brings particles together, but entanglement is the framework by which their states are shared. The study of entanglement in atomic systems continues to refine our understanding of fundamental physics. Precision measurements of entangled hyperfine states test the constancy of fundamental constants over cosmic time. Observations of entangled nuclear decays probe symmetries in the weak interaction. Even atomic clocks, which rely on transitions between hyperfine states, exploit the stability of entangled states to achieve unprecedented accuracy. Thus, entanglement is not only a philosophical curiosity, but a working principle of modern metrology. Entanglement also plays a role in the thermal behavior of matter. In condensed phases, the entanglement of electronic states across atoms gives rise to band structures in solids. Electrons in a crystal cannot be described as belonging to one atom alone, but exist in collective states that span the lattice. These delocalized entangled states explain conduction, semiconductors, and insulating behavior. In superconductors, the entanglement of electrons into Cooper pairs allows them to move without resistance. Once again, entanglement extends the rules of atoms to the macroscopic world, creating properties that no single particle could produce. One of the most profound lessons from entanglement inside atoms is that individuality dissolves at small scales. Particles retain properties such as mass and charge, but their quantum states often fuse into joint descriptions that cannot be divided. The atom is not a miniature solar system, but a web of interconnected probabilities, each part defined by the others. When you hold an object in your hand, its solidity arises from exclusions and repulsions, but the detailed chemistry that gives it structure and function arises from the entangled dance of electrons within and between atoms. This challenges the way we imagine reality. Our everyday intuition is built on separateness. Objects have boundaries, identities, and independence. But the quantum world, revealed most clearly inside atoms, resists this picture. Boundaries blur, states overlap, and information is shared in ways that cannot be unraveled. The atom, once thought to be the indivisible unit of matter, is instead a living example of unity emerging from entanglement. For a final reflection, consider that entanglement is not just a property of atoms, but of you. Every cell in your body depends on entangled electrons forming bonds, shaping proteins, and transmitting signals. Your thoughts themselves arise from entangled states in neural molecules and ions. You are not merely built of atoms, you are woven from their interconnectedness. In that sense, your very existence is testimony to the quiet, invisible entanglement that holds the microscopic world together, and in turn makes the macroscopic world possible. Chapter 7. Atoms as the memory of the universe. When we think of memory, we often imagine something held in the brain, patterns of neurons storing fragments of personal experience. Yet memory exists on far deeper levels, written into the very matter of the cosmos. Atoms are not just the building blocks of reality, but also the silent archives of history. Each atom carries within it a record of ancient processes, from the nuclear reactions in stars to the collisions of galaxies and the slow transformations of Earth. By studying atoms, their isotopes, their distributions, and their structures, we are, in a sense, reading the memory of the universe itself. The origins of atoms trace back to the first few minutes after the Big Bang. In that early epoch, the universe was an expanding plasma of protons, neutrons, electrons, and radiation. Within minutes, conditions cooled enough for protons and neutrons to fuse into light nuclei, hydrogen, helium, and trace amounts of lithium. This event, called primordial nucleosynthesis, produced the first atomic seeds. Their ratios still bear witness to that era. Today, measurements of hydrogen and helium abundances across the cosmos confirm the conditions of the Big Bang with striking accuracy. In this way, every atom of hydrogen around us is a relic more than 13 billion years old, unchanged since the dawn of time. To hold a glass of water is to touch material forged in the first minutes of the universe. Heavier atoms tell a different story, one written in the hearts of stars. Stellar fusion, proceeding over billions of years, builds elements like carbon, oxygen, silicon, and iron. When massive stars exhaust their fuel, they collapse and explode as supernovae, scattering enriched material into space. In these cataclysms, neutron capture and extreme conditions forge elements heavier than iron, such as gold, uranium, and platinum. These atoms then drift through interstellar space until gravity gathers them into new stars and planets. Thus, the calcium in your bones and the oxygen in your lungs are direct records of long-dead stars. Their existence tells a story of cycles of birth, death, and renewal on a cosmic scale. Isotopes, atoms of the same element with different numbers of neutrons, function like timestamps. Their relative abundances encode the history of nuclear reactions. For example, the ratio of carbon-12 to carbon-13 reveals the cycles of stellar burning. On Earth, isotopes serve as natural clocks. Carbon-14, produced in the atmosphere by cosmic rays, is incorporated into living organisms. When they die, the isotope begins to decay with a half-life of thousands of years, allowing scientists to date ancient artifacts. Uranium decaying into lead provides a much slower clock, measuring the age of rocks and even the Earth itself. These methods demonstrate that atoms record not only cosmic history, but also the passage of terrestrial time. The stability of most atoms is itself a form of memory. Unlike human recollections, which fade, atoms endure. A hydrogen atom formed in the Big Bang is effectively immortal unless destroyed in a stellar furnace. Even radioactive isotopes, though they eventually decay, follow precise statistical patterns that serve as chronometers. This persistence allows atoms to act as carriers of information across eons. They outlast civilizations, continents, and even stars. When scientists analyze a meteorite, they are decoding atoms that have preserved their structure since the solar system's birth. Geochemistry offers vivid examples of atomic memory. Oxygen isotopes in ice cores reveal past climates, tracking the advance and retreat of glaciers. Variations in strontium isotopes in fossils indicate the migration paths of ancient animals. Lead isotopes in minerals chronicle the history of Earth's core formation. In each case, atoms preserve conditions that would otherwise vanish without trace. The planet's memory is not written in words or images, but in the immutable ratios of isotopes. Atoms also carry the fingerprints of the environments where they formed. Stars imprint their life cycles on the atoms they create. The presence of certain isotopes in stellar spectra tells astronomers whether a star has been through cycles of hydrogen and helium burning or whether it has synthesized heavier nuclei. Distant galaxies can be studied through the absorption lines left by atoms in interstellar clouds, each line a record of conditions billions of years ago. Because light takes time to travel, we observe not only space, but also the past. Atoms along the path preserve that past in their structure, scattering or absorbing photons in ways that remain measurable even after cosmic distances. In biology, atoms act as the memory of life's continuity. DNA is a molecular archive, but its letters are written from atoms of carbon, nitrogen, oxygen, and phosphorus. These atoms were forged in stars long before Earth formed, and their persistence allows them to be reused across generations. The same carbon atom that was once part of a dinosaur's muscle may now reside in your body. Metabolic cycles shuffle atoms endlessly, but the atoms themselves retain their integrity. Life's continuity is possible because atoms endure long enough to be recycled into new forms of organization. Even within living organisms, isotopes act as silent recorders. The ratio of heavy to light isotopes in bones can reveal diet, showing whether ancient humans ate more plants or animals. Isotopic signals in hair or teeth can indicate geographic origin, as different regions carry distinct atomic signatures. Forensic science and archaeology both rely on this principle, reading in atoms the details of lives long past. Atoms, stable and indifferent, bear witness to events and movements that human memory cannot reach. In technology, we exploit atomic memory deliberately. Nuclear waste, for instance, is a reminder that atoms retain their instability for tens of thousands of years, recording human activity far beyond cultural memory. Conversely, stable isotopes in medical tracers leave behind patterns that reveal metabolic processes in the body. Even in quantum technologies, where atoms are manipulated to store and transmit information, the same principle applies. Atoms act as vessels of memory, whether of cosmic history or human design. The persistence of atoms also explains why the universe is comprehensible. If atoms were unstable on short timescales, no enduring structures could exist. Molecules would dissolve before forming, planets would crumble, and stars would burn unpredictably. The fact that atoms retain their form across billions of years allows structures to accumulate and records to be preserved. The cosmos has coherence because atoms are faithful record keepers of the conditions that made them. There is a subtle beauty in the idea that atoms are storytellers. Unlike human narratives, they do not embellish or forget. They encode history in unchanging properties, in ratios and resonances, in decay chains and spectral lines. Scientists, by developing techniques to measure these properties, have learned to read the universe's autobiography directly from its matter. Each isotopic ratio is a chapter, each atom a word in a language older than life. At the frontier of physics, researchers investigate whether atoms might also record the constancy of the laws themselves. By comparing atomic spectra from distant galaxies with laboratory measurements, scientists test whether the fine structure constant has changed over billions of years. So far, the answer seems to be no, suggesting that atoms not only preserve their own identity, but also reflect the unchanging fabric of physical law. If atoms are memory, they may be memory not just of events, but of the rules that govern events. From a cosmic perspective, atoms are thus both matter and archive. They are what things are made of, and at the same time, they are the record of how things came to be. To study atoms is to uncover stories stretching back to the beginning of time, stories that no other medium could preserve. The atoms of iron in your blood whisper of supernovae. The calcium in your bones carries the memory of stellar furnaces. The hydrogen in the water you drink recalls the first minutes after the Big Bang. For a final reflection, consider that you too are a vessel of this memory. Every atom in your body carries a history older than Earth itself. You are not only a conscious being, but also a collection of silent witnesses, each atom a survivor of cosmic epochs, each one remembering without intention. In the stillness of that thought, there is a sense of continuity. You are the present expression of the universe's past, a living archive woven from atomic memory that will persist long after your consciousness has gone. Chapter 8. The Technology of Atoms. Unlocking Reality. Atoms are not only the foundation of nature, but also the foundation of technology. Once humanity learned to understand their properties and to manipulate them, entire industries, sciences, and even civilizations transformed. The modern world is, in a very literal sense, the product of applied atomic physics. From the energy that powers cities to the microelectronics that carry information, from medical tools that save lives to the fundamental instruments of science itself, technologies built on atomic principles have unlocked aspects of reality that would otherwise remain hidden. To explore these technologies is to see how knowledge of the smallest scales reshapes the largest patterns of human life. The most widespread applications of atomic physics lie in electricity and electronics. Atoms, through their electrons, determine conductivity. In metals, valence electrons are delocalized, free to move throughout a lattice of positively charged ions. This creates electrical currents when a voltage is applied. The ability to understand and refine this behavior gave rise to the electrical age. Copper wires, steel generators, and semiconductor circuits all rely on the mobility of electrons within atomic frameworks. Yet it was the deeper comprehension of atomic band structures that revolutionized technology. By controlling how atoms are arranged in crystals and introducing impurities, doping, engineers created semiconductors whose conductivity could be switched on and off. This innovation birthed the transistor, a device small enough to fit into circuits yet powerful enough to replace bulky vacuum tubes. Transistors, multiplied billions of times on silicon chips, gave rise to modern computing. Every phone, computer, and digital system exists because of our ability to manipulate electrons in atoms with exquisite precision. Lasers are another iconic atomic technology. They rely on the principle of stimulated emission, first predicted by Einstein. When atoms or molecules are excited to higher energy states, they can be induced to release photons coherently when stimulated by incoming light of the right frequency. The resulting beam is monochromatic, coherent, and directional, unlike ordinary light. Lasers now permeate nearly every aspect of life. They read barcodes, perform delicate surgeries, enable fiber optic communication, and measure distances with extraordinary accuracy. At the core of each application is the quantized energy structure of atoms and the controlled release of photons. What began as a theoretical possibility has become an indispensable technology that redefined information transfer, medicine, and manufacturing. Medical imaging also springs directly from atomic physics. X-rays exploit the ability of high-energy photons to penetrate tissues differently depending on atomic composition. Denser materials like bone absorb more, producing contrast. Nuclear medicine uses isotopes that undergo radioactive decay, emitting particles or photons that can be detected outside the body. Techniques like positron emission tomography trace the movement of radioactive isotopes through tissues, offering a view of metabolism and function rather than just structure. Magnetic resonance imaging, one of the most powerful diagnostic tools, relies on nuclear spin states. By aligning the spins of hydrogen nuclei in a magnetic field and perturbing them with radiofrequency pulses, doctors can build detailed maps of soft tissues. Each of these technologies translates atomic properties into visualizations that extend human perception beyond natural limits. Atomic clocks represent another profound application. By exploiting the hyperfine transitions of cesium, rubidium, or strontium atoms, scientists define the second with extraordinary precision. The oscillations of atoms are stable in a way no pendulum or quartz crystal could ever achieve. Modern optical lattice clocks reach accuracies so extreme that they would not drift by more than a second over the entire age of the universe. These clocks underpin the global positioning system, which relies on precise timing to triangulate positions on Earth. They also allow measurements of relativistic effects, detecting differences in the passage of time at varying altitudes. Thus, atomic clocks not only guide navigation, but also test Einstein's theories and explore the fine structure of reality itself. Nuclear energy, though often controversial, is perhaps the most dramatic application of atomic transformations. In nuclear reactors, the fission of heavy nuclei such as uranium-235 releases immense energy, millions of times more per reaction than typical chemical processes. This energy, harnessed in controlled environments, generates electricity for entire cities. Nuclear power offers a low-carbon source of energy, though it brings challenges of radioactive waste and safety. Fusion, the process that powers stars, remains a technological goal. If achieved on Earth in a practical and sustainable way, fusion would provide vast amounts of clean energy by fusing light nuclei into heavier ones. The pursuit of this technology reflects humanity's attempt to replicate and control the processes that light the stars. Analytical tools based on atomic principles have also unlocked scientific discovery. Mass spectrometry sorts ions by their charge-to-mass ratios, identifying isotopes and molecules with high precision. Atomic absorption spectroscopy measures the concentration of elements in samples by detecting characteristic frequencies of light absorbed by atoms. Neutron scattering, relying on interactions between neutrons and atomic nuclei, reveals the structure of materials at the atomic level. These techniques transform atoms into messengers, carrying information about composition, structure, and dynamics. They have been crucial in fields ranging from chemistry to geology to biology. Even information storage is deeply tied to atomic behavior. Hard drives use magnetic domains created by the orientation of electron spins in atoms. Optical discs rely on materials that respond predictably to lasers. More recently, scientists have explored atomic-scale storage, where individual atoms on a surface represent bits of information. Quantum computing, still in its infancy, harnesses entangled states of atoms or ions as qubits, capable of performing calculations that classical computers could not achieve in any reasonable time. These technologies highlight a trajectory. As our ability to manipulate atoms improves, the frontier of information science shifts from the macroscopic to the microscopic, and eventually to the quantum domain. Nanotechnology takes atomic control further still. By designing materials atom by atom, researchers create substances with tailored properties. Carbon nanotubes, graphene sheets, and engineered nanocrystals owe their extraordinary strength, conductivity, or optical behavior to atomic arrangements. These innovations hold promise for everything from stronger materials to targeted drug delivery. Atomic-scale engineering thus moves beyond understanding the world to actively shaping it with precision. One of the most striking features of atomic technology is that it often pushes the limits of measurement itself. The scanning tunneling microscope, for instance, uses quantum tunneling currents to image surfaces atom by atom. The atomic force microscope senses the tiny forces between atoms on a surface and a probe tip, creating topographical maps with near-atomic resolution. These tools not only allow us to see atoms, but also to manipulate them, arranging them into patterns and structures. Such techniques demonstrate that we are no longer passive observers of the atomic world, but active participants, rearranging matter at its most fundamental scale. The role of atoms in energy, communication, medicine, and computation demonstrates that atomic physics has become an applied science with global impact. But beyond utility, these technologies also expand our perception of reality. They allow us to see deeper into the body, further into space, and more precisely into time. They make visible what was invisible, measurable what was inaccessible, and controllable what was once untouchable. In this sense, atomic technology does more than serve human needs. It enlarges the boundaries of what reality means to us. There is a cautionary side to this story as well. Nuclear weapons represent the destructive potential of atomic mastery. The same physics that provides clean energy in reactors unleashed devastation in Hiroshima and Nagasaki. Even peaceful technologies carry risks: radiation exposure, nuclear waste, and proliferation. The lesson is not that atomic technology is inherently dangerous, but that its power magnifies human choices. In learning to unlock atoms, humanity also accepted a responsibility to wield that knowledge wisely. Despite such risks, the benefits are undeniable. The electronics that allow you to read this text, the medical scans that save countless lives, the satellites that guide navigation, and the scientific discoveries that deepen our understanding all depend on the application of atomic knowledge. What once seemed impossibly abstract, confined to blackboards and equations, has become the very infrastructure of modern existence. And in a more subtle way, atomic technology reflects something profound about humanity. Atoms existed long before life, stars, or planets. For billions of years, they acted only according to natural laws. But through science, those same atoms became tools of consciousness, bent to new purposes. The silicon in computer chips was forged in ancient stars, yet today it carries human thought as electrical signals. The uranium deep within Earth's crust was born in supernovae, and now it powers cities. The hydrogen atoms that once floated in the infant universe are now measured in atomic clocks that tell us the time with cosmic accuracy. For a final reflection, consider that in mastering atomic technology, humanity has learned not just to survive, but to alter reality itself. Every laser pulse, every transistor switch, every scan of an atomic microscope is an echo of our ability to translate invisible rules into tangible effects. You are surrounded by the hum of atoms working not just as nature designed, but as human ingenuity has guided. And in this quiet dance between the natural and the engineered, you glimpse something extraordinary. Atoms, once silent foundations of matter, now serve as partners in unlocking the very reality they compose. Chapter 9. The Limits of Atomic Physics, Where Reality Blurs. Atomic physics has been one of the greatest triumphs of modern science. It provides a framework that explains why matter is stable, why chemical reactions occur, and why light interacts with matter in precise, predictable ways. The theory of quantum mechanics, developed to describe atomic behavior, has been confirmed by experiment to extraordinary accuracy. It accounts for the structure of the periodic table, the properties of semiconductors, the behavior of lasers, and countless other phenomena. Yet for all its success, atomic physics is not the final word on reality. Its power lies in describing atoms as bound systems of electrons, protons, and neutrons, governed by electromagnetism and quantum rules. But this framework has boundaries. Beyond them, the clarity begins to blur, and deeper mysteries appear. One of the clearest limits arises in the description of nuclei. Atomic physics usually treats the nucleus as a compact, charged object around which electrons arrange themselves. This approximation works well for calculating spectra and chemical behavior, but it leaves unanswered the detailed structure of the nucleus itself. Protons and neutrons interact through the strong nuclear force, and their arrangement influences the sizes, shapes, and stabilities of nuclei. While nuclear physics extends the picture, the boundary between atomic and nuclear domains is not always clean. For example, hyperfine structure and spectra, used in atomic clocks, depends on the spin interactions of nuclei, tying nuclear properties to atomic behavior. Thus, the atomic description cannot stand completely alone. Another limit appears when atoms interact with extreme environments. In ordinary conditions, electrons occupy stable orbitals, but in strong magnetic or electric fields, these orbitals distort, shift, or even collapse. Inside white dwarfs or neutron stars, atoms cannot exist in familiar forms. Electrons are forced into exotic states, sometimes merging into collective seas that defy conventional atomic pictures. At densities found in such stars, the pressure from electrons, called degeneracy pressure, takes over, and atoms cease to resemble the independent units we study in laboratories. The very concept of an atom as a discrete building block loses meaning in these extremes. Even within laboratory conditions, atomic physics reaches its limits when faced with relativistic effects. For light elements, non-relativistic quantum mechanics provides a good description. But for heavy atoms with many protons, the inner electrons move at speeds approaching the speed of light, requiring relativistic corrections. Without including relativity, predictions for gold's color or Mercury's liquid state would be incorrect. Gold appears yellow because relativistic effects shift the energy levels of its electrons, altering how it absorbs and reflects light. Mercury remains liquid at room temperature, partly because relativistic contraction changes its bonding properties. These examples show that atomic physics cannot be divorced from relativity if we seek accuracy in the heaviest elements. Another frontier lies in quantum electrodynamics, QED, the quantum theory of how light interacts with charged particles. QED extends atomic physics by including the fluctuations of the vacuum itself. The Lamb shift in hydrogen, a small difference in energy levels, arises from interactions between electrons and the ever-present quantum vacuum. The theory predicts such effects with remarkable precision, and experiments confirm them to many decimal places. But as we probe more deeply, even QED shows limits. At extremely high energies or in strong fields near black holes, our current frameworks may no longer suffice. New physics may emerge, uniting QED with other forces in ways not yet known. Atomic physics also struggles when confronted with gravity. Electrons, protons, and neutrons all have mass, so gravity should influence them. But the effect is so weak compared to electromagnetism that it is usually ignored. For laboratory atoms, this is an excellent approximation. Yet in a complete theory of reality, gravity must play a role. Efforts to unify quantum mechanics with general relativity remain among the greatest unsolved problems of physics. Atoms, so well explained by quantum rules, exist within a universe shaped by gravity, and the absence of a coherent framework that unites the two marks a profound limit of atomic theory. Dark matter adds another boundary. Observations of galaxies and cosmic structure show that most of the universe's mass is not made of ordinary atoms at all. Atomic physics, with its detailed understanding of electrons and nuclei, explains only a minority of the universe's matter. Dark matter does not emit, absorb, or scatter light in ways atoms do. If it interacts through atomic-like forces, those interactions must be exceedingly weak. The familiar picture of atoms as the fundamental building blocks of matter is, from a cosmological perspective, incomplete. Most of the universe's building blocks remain outside its scope. Even within atoms themselves, quantum uncertainty sets limits. We cannot know an electron's position and momentum with unlimited precision. Instead, we work with probabilities and distributions. This has not prevented extraordinary predictive power, but it means that atomic physics cannot ever provide deterministic answers to every question. The randomness of radioactive decay, the probabilistic outcomes of quantum measurements, and the spread of possibilities in electron distributions are features, not bugs, of the theory. The limits here are conceptual. Reality at the atomic level is not the clockwork predictability once imagined, but a blurred tapestry of probabilities. There is also a practical boundary, computation. Solving the equations that govern even modestly complex atoms or molecules is a monumental challenge. Exact solutions exist only for hydrogen. For helium and beyond, approximations and numerical methods must be used. The many-body problem, describing systems of multiple interacting electrons, becomes overwhelmingly complex. Advances in computational methods and quantum simulations improve our reach, but the difficulty underscores that even with complete equations in hand, our ability to apply them has limits. The richness of chemistry arises from these many-body interactions, but the full solution of atomic physics for complex systems remains out of reach. As physics pushes into new realms, we find that atomic physics sits between two vast domains. On one side, it emerges from particle physics, where quarks, gluons, and fundamental fields rule. On the other, it merges into condensed matter physics, where trillions of atoms behave collectively in ways that create entirely new phenomena. Between these extremes, atomic physics provides clarity, but its edges blur. Quarks are confined inside nucleons, and atomic theory does not explain why. Superconductivity and magnetism emerge in materials, and while atomic rules contribute, they are not sufficient alone. Atoms provide the bridge, but the full landscape requires theories both smaller and larger than atoms themselves. Philosophically, the limits of atomic physics remind us that explanations are layered. Atoms once seemed indivisible, ultimate foundations. Then nuclei were discovered, then quarks, and still deeper mysteries remain. Each advance in physics reveals that what seemed fundamental is in fact emergent from something deeper. Atomic physics remains essential, but it is not absolute. It is a chapter in the book of reality, not the whole text. This recognition does not diminish its achievements. The fact that atomic theory can predict spectral lines to astonishing accuracy, explain the stability of matter, and enable technologies from lasers to quantum computers is extraordinary. But its boundaries encourage humility. They show that no description is final, and that science advances not by finding ultimate truths, but by progressively refining the scope of understanding. Where atomic physics blurs, new physics waits to be uncovered. Chapter 10. You are a temporary arrangement of atoms. The story of atomic physics ultimately circles back to us. Atoms, forged in the fires of stars and shaped by the laws of quantum mechanics, have come together to form every object, every living being, and every thought. To say you are an arrangement of atoms is not poetry, but scientific fact. What gives this statement weight is not only its accuracy, but its impermanence. The arrangement that constitutes your body and mind is temporary, a momentary structure in the long timeline of the universe. Atoms endure, their configurations do not. Each atom in your body carries its own history. The hydrogen in the water that sustains you dates back to the Big Bang itself. The carbon that makes up your tissues was synthesized in stars that lived and died billions of years ago. The iron in your blood was created in supernovae, scattered across space before being drawn into the cloud that formed the solar system. These atoms traveled through countless transformations before becoming part of you. None were created for the purpose of forming your body. Their presence here is the outcome of natural processes guided by fundamental forces. And yet the arrangement matters. The way atoms are organized gives rise to structure and function. DNA is a sequence of carbon, nitrogen, oxygen, hydrogen, and phosphorus atoms, arranged so that they encode instructions for life. Proteins are elaborate patterns of amino acids, each folded into shapes dictated by atomic interactions. Neurons transmit signals through the movement of ions, themselves atoms stripped of electrons. Every heartbeat, every thought, every sensation you experience is the outcome of interactions between atoms obeying the same rules that govern stars and crystals. What distinguishes you from a rock is not the atoms themselves, but the order they form, the arrangement that persists long enough to sustain life. The arrangement is fragile. Atoms in your body are in constant motion, exchanging with the environment. The oxygen you inhale, the carbon dioxide you exhale, the food you eat, and the water you drink are all exchanges of atoms. Even within your body, atoms are shuffled and replaced. The calcium in your bones cycles, the hydrogen in your cells trades places with water, and the nitrogen in your proteins turns over as molecules are broken down and rebuilt. In a matter of years, most of the atoms in your body will have been replaced. Continuity of self is not continuity of atoms, but continuity of pattern. This dynamic rearrangement underscores the temporary nature of embodiment. Atoms that compose you today may tomorrow reside in soil, in the air, or in another living being. Life is recycling at the atomic scale. Ecosystems depend on this flow. Plants capture carbon atoms from the atmosphere, animals consume plants, and decomposers return atoms to the soil and air. The carbon you exhale may one day feed a tree. The nitrogen in your muscles may one day fertilize the ocean. Atoms persist through these cycles, but the forms they take are transient. Your existence is one phase in the journey of atoms, a chapter in their unending circulation. Biology provides striking timescales for this turnover. Red blood cells, for example, live only about 4 months before being recycled by the spleen. The atoms that formed them are then reused to make new cells. The lining of your stomach is replaced every few days. Even the hard enamel of your teeth incorporates atoms that once flowed through food and water. Estimates suggest that in less than a decade, the majority of the atoms in your body will have been exchanged. You are not a static collection of matter, but a river of atoms flowing through a form. Physics reinforces this view. Atoms are stable not because they are immutable, but because their structures are governed by balanced forces. Electrons resist collapse due to quantum exclusion. Protons and neutrons are bound by the strong force, and their collective stability defines matter. But atoms themselves are not indestructible. Radioactive decay shows that nuclei can transform, fission can split atoms, and fusion can combine them. The atoms of your body will not remain as they are forever. Some will decay, some will be incorporated into new molecules, and some may eventually be consumed in the life cycle of stars. Stability at the atomic scale is long compared to human life, but even here impermanence rules. The impermanence is matched by universality. The same atoms that constitute you also constitute the oceans, the mountains, and the air. The laws that bind them are the same everywhere. The difference lies only in arrangement, in how atoms combine and interact. A diamond and a lump of graphite are both carbon, yet their properties diverge radically because of how the carbon atoms are bonded. Likewise, the line between living and non-living matter is not in the atoms themselves, but in the dynamic patterns they form. Life is not a special kind of matter, but a special kind of organization. On Earth, this organization is mediated by cycles that connect every living thing. The carbon cycle moves atoms through air, ocean, rock, and life. The nitrogen cycle binds atmospheric nitrogen into molecules that nourish plants, which in turn nourish animals, before bacteria return the atoms to the atmosphere. Even rare elements like iodine and selenium trace cycles through ecosystems, making brief appearances in human tissues before moving on. The air you breathe contains argon atoms that have cycled through countless lungs over millions of years. The water you drink holds hydrogen and oxygen atoms that once passed through glaciers, rivers, and perhaps other organisms. Understanding this does not diminish the significance of human life, but places it within context. The complexity of your body, the richness of your thoughts, and the depth of your emotions all arise from interactions of atoms guided by the same principles that shape stars and galaxies. That such simplicity can give rise to such complexity is one of the central wonders of physics. It shows that the universe is not only capable of creating matter, but also of arranging it in ways that allow self-awareness. Technology allows us to manipulate atomic arrangements directly, creating patterns never found in nature. From silicon microchips to synthetic molecules, humanity rearranges atoms into forms that serve new functions. These creations, though artificial, follow the same rules as natural arrangements. In doing so, we become active participants in the atomic story, shaping matter rather than simply inheriting it. Even so, our creations are subject to the same impermanence. Machines wear down, molecules degrade, and materials decay. The atoms remain, but their order does not. On cosmic timescales, even the atoms themselves may not endure. Protons are believed to be stable for longer than the current age of the universe, but some theories suggest they might eventually decay over unimaginable spans of time. If so, the universe's memory of atoms would also fade. Stars will burn out, galaxies will thin, and matter itself may dissolve into radiation and subatomic remnants. The arrangements we call life are short-lived against this backdrop, flickers of order in an expanding cosmos, and yet, Impermanence does not negate significance. Atoms are temporary in their configurations, but their capacity to form complex arrangements makes existence possible. You are not just a collection of hydrogen, carbon, oxygen, and nitrogen. You are the outcome of billions of years of cosmic history, arranged into a form that can reflect on its own origin. That reflection, though fleeting, is real. For a final thought, consider that your atoms have traveled across time and space to be here, now, in this arrangement. They have passed through stars, oceans, rocks, and living beings, and will continue their journey long after you. You are their present pattern, one among countless others, brief but luminous. In that sense, to live is to participate in the great unfolding of the universe, a temporary but extraordinary arrangement of atoms that for a while becomes aware of itself. Thank you for staying with me, my friend. You've just traveled through the quiet mysteries of atomic physics, a story written into every breath and every star. If you're still awake, another video awaits you. Let it guide you deeper into the cosmos. And if your eyes are already heavy, may you rest peacefully. Sweet dreams among the stars.